lecture for lecture number 3, Introduction to Mega Functions, Numerically Controlled Oscillators, or NCOs, and we'll also discuss some important issues around synchronization and edge detection. Okay, so the reason we bring this up in this lecture is because it's fairly crucial to something that we want to do with the NCO. So we're going to talk about issues around synchronizing asynchronous signals. For example, if you push the push button, you get a negative edge, and really you want to synchronize that with the regular rising edge of the clock. If you don't do that, you can have instability and your design might not work properly. So there is a industry standard way of resolving this problem called synchronization, and we'll discuss that towards the end of this lecture. Right, first of all, let's do a very quick introduction to mega functions. Okay, so I've talked about these before, but mega functions are inbuilt modules within Quartus, and you can generate them, and then they become, well, you're able to instantiate them within your design just like any other module, but you don't get to see the HDL code that make them up. That's kind of hidden, and it's all driven by IP. So if you are developing a system commercially, you do have to pay to use these mega functions. But for us academic users, we are free to use these functions as we wish without having to pay. And they do come with great functionality. So these are the 6 mega functions that sort of spring to mind when I think about the powerhouse mega functions within Quartus. So we've got the phase locked loop. So the phase locked loop is able to change a clock frequency, and it's also able to introduce a phase shift into into clocks as well, which is important when you try to interface to things like SDRAM, because you're trying to compensate for the delay of the signal as it travels between 2 chips on the board. The numerically controlled oscillator, or NCO, that's the one we'll focus on today. The FFT, we'll focus on the FFT in lecture 5, I believe. So I won't say too much about that one now, except that it's a fascinating mega function with lots of great applications. We've got the FIR, finite impulse response filter, which is basically a digital filter, and again, really useful, really powerful mega function. And then we've got the Chordic algorithm. The Chordic allows you to change the real and imaginary components of a signal into phase or vice versa. Okay, so again, incredibly useful in many applications, especially in communication systems. And then we've got the RAM and the ROM. So that's memory-based mega functions where you can store samples into memory and then access them as you wish. Okay, now I do have a video on these mega functions on Learning Central, so make sure you watch that video for a proper introduction to these mega functions. Now, the numerically controlled oscillator, that's the focus of today's lecture. It's an incredibly useful mega function, and the basic idea of the NCO is it allows you to generate a digital sinusoidal wave at a user-defined frequency. And this frequency, if you look at equation 1 here, the frequency of the sine wave depends on the frequency of the clock. That's the square clock that goes into the NCO. The phase increment value, that's like an input to the NCO, and that's actually what we can vary to change the output frequency. And N is something called the accumulator bit width, which is another variable in the NCO. It's not really a variable, it just means it's the number of bits of the phase increment. So now we've got the ability to generate a sinusoidal wave at an arbitrary magnitude resolution and an arbitrary frequency just by varying this phase increment. And this is a very powerful technique It's used extensively in signal generators. So the signal generator in the lab is probably using an NCO, and it's also very useful in communication systems where you need to generate a sine and a cosine wave. So that's the one we're going to look at today. Now, there's an example here of how to work out the phase increment value that you need to generate a particular output frequency. So let's say we wanted to make a 500 kilohertz sine wave, and the input clock was 5 megahertz, that's the square clock, and the accumulator bit width was 32, we can just apply this equation and it would tell us what number we need to input into the NCO in order to get this frequency. And there's nothing stopping us changing that frequency in real time. Okay, so we can change this number whenever we want. We can make that number variable, it can go up or down, and that will change the output frequency of the NCO. In fact, in the lab, that's exactly what we're going to do. Okay, we're going to link the push buttons to this phase increment value. So if we push the push button, it will increase or decrease this phase increment value, and that will change the output frequency of the NCO. So that's going to be an interesting thing we do in the lab. Now, the architecture of the NCO is actually quite simple. It's based on a phase increment value, which feeds into a phase accumulator. And the way it works is that phase increment value determines the slope of the sawtooth wave, because all we're doing in the phase accumulator is just adding that phase increment to itself again and again and again. So it grows as a sawtooth wave. That sawtooth wave becomes the input to the waveform generation unit, and that converts that sawtooth wave into the sine and the cosine waves. The complexity in the NCO is actually in this waveform generation unit, and there's 3 or 4 different options we can use to generate a waveform generation unit. One of them is to use memory. Using lookup tables, we can work out exactly what input it corresponds to the sample on the sine wave, and we can just keep looking using the lookup table to generate the sine wave. The other option is to calculate this as we go, and we can use the Cordic algorithm to do this. It's always a trade-off between the amount of logic elements we use and the amount of memory. Okay, so with the lookup table, ROM-based approaches, we use lots of memory. With the Cordic, we use lots of logic elements. And with the DE0 Nano, we have to use the Cordic or multiplier-based architecture, because it just doesn't have the memory capability, the sheer number of memory bits to implement a large ROM waveform generation unit. So really we're forced to use the Cordic or the multiplier-based NCO architecture. So this is a very simple NCO design. Okay, so we've got a 50 megahertz input clock, and then we're using a phase locked loop to increase the clock frequency to 100 megahertz. And then we use a wrapper module, which its only purpose really is to instantiate the NCO within it. And it makes it easy for us to then input a phase increment value. Okay, so that's where we put the NCO. And then if we give it a particular phase increment value, it will give us a sinusoidal wave. And it's important to recognize at this point that this sinusoidal wave is digital. Okay, it's a digital sinusoidal wave that's going to have a particular resolution. Okay, that resolution is dependent on the number of bits, the magnitude resolution. Okay, so whether you use 12 bits, 14 bits, 18 bits, the more bits you have, the better your resolution. The other thing you have to think about is the period of your signal, or the period of the output sinusoidal wave in relation to the input clock frequency, because that 100 megahertz is essentially your sampling rate for that sinusoidal wave. So if you choose, well, let's say you have a 100 megahertz clock, and then you ask for a 50 megahertz sine wave. Well, that's only going to give you 2 samples per period. So that's going to be an awful looking sine wave. So typically you want the clock to be at least 10 or 15 times higher than the output sinusoidal frequency. That's nothing to do with Nyquist. That just gives you a much nicer, smoother looking sine wave. Okay, but essentially NCOs, very easy to use. You just instantiate it and you give it a particular phase increment value to get the frequency that you want. Okay, that's a simple NCO design. Now, to generate the NCO, I've actually got 2 examples of this on Learning Central. Okay, so I've got one simulation-based example where we simulate the NCO using Model Sim, and then there's also, well, I don't think that second example is the NCO. Is it the NCO? I forgot now, but I'm sure that there's a second example on Learning Central that goes through the programming design flow to implement the NCO on the DE0 Nano. And of course, the lab, this is what we'll be doing in Lab 3. Okay, so the aim of that lab is to generate a sinusoidal wave and then inspect that wave using Signal Tap. Okay, so this is a screenshot of the IP parameter editor. So this is during the process of generating the NCO. And you can see we've got a couple of variables here that we can set. Okay, so the phase accumulator precision, that's 32 bits in this case. Okay, and that's basically the N here. Okay, so that makes a difference to the output frequency that we get. Then we've got the angular resolution. Okay, the higher that is, the more accurate your sine wave will be. And then we have the magnitude resolution, and that determines the resolution in bits of the output sine wave. Okay, so how many bits the digital samples that the NCO generates, that's set with this number. Then we've got here the clock rate and the desired output frequency. And then it gives you the phase increment value that will give you that output frequency for that clock. Now, this does nothing to the generation of the NCO. It changes nothing. It's just an easy way for you to work out what phase increment you need given a particular clock rate and a particular desired output frequency. But there's no reason to use that if you know this formula, because you can just calculate it this way. Okay, so that's the IP parameter editor. So watch out for this in the lab. Now, simulating the NCO, I don't need to talk about this too much because there's an example video on Learning Central going through the simulation. This is the test bench. So watch that video, and if you're a bit rusty with the the simulation design flow, watch that video carefully because it goes through the full simulation design flow. So there's no need for me to talk about it in detail here. One thing I will say though is this is how you instantiate the NCO. So this is instantiated within a test bench. If you program the board, or if you go through the programming design flow, this is the same way that you would instantiate the NCO within the wrapper module. Okay, so very, very straightforward. Now, this is the variable signal generator using the NCO, and this is the design. This is the design that we aim to implement within the lab. And what we want to do is use the two push buttons to either increase or decrease the phase increment value. Okay, and if we do that, of course, the output frequency will change. So this gives us a variable, controllable output sinusoidal frequency. Okay, but there are some complications with this design. To actually change the phase increment register based on two possible push buttons, okay, which are they start off one, and then when you push they go low. It's not intuitive at all to do this in hardware. Okay, so during this lecture I want to talk about some very important issues regarding how to convert a falling edge into a pulse. And that's a very common thing, a very common requirement in HDLs. Okay, so that's what we'll look at very closely in both in the lab, and we'll have a look at a few examples in this lecture as well. Okay, so this is not as intuitive as you might think. So this is the wrong way of doing this, okay? So let's just assume that what we want to do is change this phase increment value, okay? Because remember, that phase increment determines the output frequency, okay? And that's an input to the NCO, okay? So the higher this is, the higher the output frequency, and the lower it is, the lower the output frequency. And if we can add to this number or take away from that number, we will increase or decrease the output sinusoidal frequency. So this is one attempt at performing that task, but this is the wrong way of doing it. And I think it's really important that we understand why this is the wrong method. And the reason it's the wrong method is because we're trying to do something which is not possible in hardware. Okay, it's actually not possible to have two negative edges in the sensitivity list, because that would imply a D-type flip-flop which has two clocks. Okay, if we assume that push button 1 and push button 2 are clocks. Okay, that's not possible in hardware. Okay, so if you tried this in quarters, it would give you an error, and it would say you're trying to drive a register from two clocks. Okay, so that's the wrong way of doing it. This is a better way of doing it. This is called a falling edge detector. And what this piece of hardware does is it recognizes when you have a falling edge. And the way it works is in the red here we have the push button press. Okay, that's what happens when we push the button. It goes from 1 to 0, and this hardware detects that falling edge, and it gives us a pulse, like a flag, which tells us that it's detected a falling edge. And the way it works is when we press the push button goes into the D-type flip-flop. So push button old is the push button, but one clock cycle delayed. So that's why it's called here push button old. Okay, it's a delayed version of the push button. That gets compared with the current push button signal inversed. Okay, and if you do that, you'll find that for a small amount of time, both of those signals will be 1. And under that condition, we have detected a falling edge. So just think about that for a while. And this is also why we have an AND gate here, because if both of them are 1 for a short amount of time, that would actually give us a pulse. Okay, that pulse would go high when both of the inputs to the AND gate are 1. Otherwise, all other conditions, it's 0. Okay, so this is a very neat way of doing falling edge detection. Okay, to do rising edge detection is something slightly different, but a very similar concept. Okay, and look at the code here. So this code is the Verilog implementation or the Verilog representation of this hardware. Hopefully you know enough by now to recognize that that this Verilog code would give you this hardware. Okay, so that's a falling edge detection. And with regards to this design, there is an example on Learning Central. So I think it's example 2 programming, where I go through the programming design flow for this design. Okay, so make sure you watch that video. It's only, I think, about 10 minutes long. I try to keep those ones as brief as possible, but that's the programming design flow for this falling edge detector. However, I am not satisfied with this falling edge detector as it is, okay? And I'm going to explain, or try to explain, why this falling edge detector is not a good design. Okay, so now if you think about the way this design actually works, the trigger that's telling the upstream logic that we've detected a falling edge, that will go to 1 whenever the not push button and the push button old are both 1, because it's an AND gate. So 1 and 1 is 1. At all other times, that trigger is on 0. But it's interesting because the push button, that could come in at any time relative to the clock. Okay, and that's a big problem, because if that push button comes in a bit later, it will affect how wide that trigger pulse actually is. Okay, and that could spoil the integrity of the upstream logic, because perhaps that trigger pulse will now be too narrow for the upstream logic to actually detect it. Okay, so that's a really important consideration when we think about how we combine asynchronous signals, like the push button could happen at any time. It's not synchronized to anything other than when the user decides to push that button. How do we combine that with our synchronous logic? That's the kind of logic that we like, because everything is synchronized to the rising or falling edge of a clock. In this design, we've got a big problem, okay? And I'm actually going to show you a design. Okay, I've actually modified this falling edge example, and I've added signal tap. Okay, so if we go to Learning Central, I'm going to open falling edge bad signal tap. Okay, this is a development of our very bad design. Okay, so I'm just going to open up that archived file within Quartus, and I'm going to take a look at the BDF. So all I've done with this design is I've added a phase locked loop, and that PLL is decreasing the clock frequency to 2 megahertz. Okay, so this point here is a 2 megahertz clock. Okay, now this input clock, of course, is still 50 megahertz. And the reason I've done this is so I can actually see, I can visualize the trigger in signal tap. Okay, because we can trigger signal tap and we can clock signal tap at the fast clock, and that will allow us to see the phase shift of the slower clock. Okay, and what we're looking for is the width of that trigger signal. Okay, so I'm going to open signal tap, and this is incredibly important, by the way. So let's compile. Okay, if you unarchive a project, you have to recompile, unfortunately. Okay, so let's recompile. It doesn't take very long. And what we're looking for, as I said before, is the width of that trigger pulse. In this very bad design, I'm predicting that that trigger pulse will be variable because it depends on where the falling edge of our push button is relative to the rising edge of the clock. Okay, and it's important because the next step in this design, as I explain in the example, is a block here which is synchronous to the clock, and it's looking for that trigger. So at the positive edge of the clock, it's looking for the trigger. If that trigger is 1, we increment the count. If trigger 2 is 1, we decrease the count. Okay, but that trigger might not be where this block expects it to be. Okay, so we're going to get unpredictable behavior. Right, okay, so let's program the device. And the important thing about this signal tap design is the trigger, as you can see here, is on the rising edge of the signal called trigger. And that's at the center of the waveform window. Okay, so when I push the button, that should trigger signal tap, and we should see all of the waveforms around that trigger. It's exactly the same as how a normal oscilloscope trigger works. Okay, let's run it. So it's waiting for trigger, it's waiting for that rising edge, and I'm going to press the push button. Right in the middle of the waveform, you can see our signals are changing. Now you can see the trigger. We do have a pulse. I'm going to press it again, and we're going to see the variability. If I just zoom out a bit, actually, this bottom one is the clock, and the trigger, you can see, is significantly narrower than the clock period, and that's not good for the upstream logic. I'm going to press it again. That one is bigger. Okay, so we've got lucky with that one. That's a fairly wide pulse. Try again. Again, another wide one. And I'm going to keep on pressing it so you can see the variability. Okay, it's completely dependent on where the falling edge of the push button is relative to the rising edge of the clock. Okay, and the reason that's the case, have a look at this timing diagram. As I said before, the trigger is the AND of push button old and not push button. Okay, that's what this line of code is doing. Okay, and that is completely dependent on how long both of those signals are one. And if you think about it, that is completely dependent on where this push button happens to be relative to the clock. That's not what we want with our design. Okay, we want this trigger to be a reliable width, and preferably we want that to be 1 clock period. Okay, the answer is to use what's known as a synchronizer stage. Okay, and it's very simply, it's 2 cascaded D-type flip-flops. And what these 2 D-type flip-flops do is they synchronize the falling edge of the push button to the clock on the FPGA. And if they're synchronized, we get a much more reliable pulse at this point. Okay, to understand why, take a look at the timing diagram. Okay, this is push button asynchronous. That's the raw falling edge of the push button, and that could happen anywhere within the clock period. Okay, now that first D-type flip-flop, it synchronizes that falling edge to the rising edge of the clock, and then the next D-type flip-flop does exactly the same thing. It synchronizes it to the next rising edge of the clock. And we can guarantee at this point, okay, because push button sync to old, we can guarantee that that is going to be, it's going to be 1 clock period delayed as compared to not push button sync to. So we're guaranteeing with this design that the trigger is 1 full clock period every single time. Okay, it's a difficult concept to get your head around, but this is the classic problem of synchronizing an asynchronous signal, which is not synchronous to anything in your design. What you want to do is bring that in and synchronize it to the clock in your design. And this is exactly what you do. Now we're using a push button here, but this concept applies to many other things that you might need to do in Verilog. And I've actually got proof that this works. Okay, I've got another design. Okay, this one is sync falling edge signal tap. I'm going to open this design. So I would encourage you to open these designs and play with them yourself. You've got everything you need. You've got the board, you've got the software, so you can actually play with these designs. So let's have a look at files. Very similar design, except this time we have those two synchronizer stages. Okay, it's just non-blocking assignments, which in hardware are D-type flip-flops. Okay, so you can have a look at this code, satisfy yourself that this is two D-type flip-flops. Okay, and as I said before, it's duplicated, okay, because we've got two push buttons. Okay, so everything happens twice. Okay, so what we're going to do is open Signal Tap. I think it would make sense if I close Signal Tap from the previous design. So you have to stop it and then close Signal Tap, and then is this the new one? Yeah, okay, so let's just tidy that up a little bit. So let's open Signal Tap. It's Tools, Signal Tap Logic Analyzer. And again, we have to run compilation, unfortunately, because it's an unarchived project and that requires a new compilation. So what I'm looking for with this more robust design with the synchronizer stages is reliability of the width of that trigger pulse. And ideally, we want that to be one full clock period, because that gives us the best chance upstream of capturing that signal if we use an always at negative edge of clock block. Okay, it gives us the greatest amount of grace either way, and it might not make that much of a difference in a very simple design like this, but when you have a complex design, things like this do make a difference, because, you know, especially high speed designs, you need to do this. Okay, so let's open up, I'll get Signal Tap back again, program with our new programming file that compilation has just produced, and then we will auto run analysis. It's waiting for trigger, so I'm going to push the button, push the button, push the button. You can see the falling edge, that's the push button signal, that is still kind of random in relation to the clock, which is at the bottom. So as I press the button, have a look how the push button falling edge is moving in relation to the clock. But now it doesn't matter, because we have those synchronizer stages, the important signal, trigger, that is absolutely rock solid, and it's one full clock cycle. So if we have an upstream module, as we do, and that's looking, that's registering this value on the negative edge of the clock, that's right in the middle of that pulse. And that's exactly where you want to be, because that's where the signal is most stable. Okay, so this is fundamental digital design, signal integrity, metastability, synchronization. Okay, so very important concept. I'll go over this again in Friday's lecture, but please spend some time looking at those timing diagrams, playing around with this design. I know we're just using a push button, but we have unearthed one of the most important concepts in digital design. Okay, so I'll see you in the lecture.